Chapter number 20, rates of reaction. Now, reactions can vary in speed, just like given over here. Some reactions happen in fraction of seconds. For example, explosions. For examples are glorious fireworks, sometimes dissolving of tablets in water. For those specifically, we need a solution to drink. And rusting may take days or weeks. Volcanic formation or weathering of rocks may take a very long time, like decades, or maybe sometimes centuries. So some reactions are pretty slow, some reactions are pretty fast. How can we say that a reaction is slow or a reaction is fast? That would be considered in this chapter, rate of reaction. To begin with, we design experiments to measure the rate or speed of reaction. Now, when I use the word speed, it usually relates to a physics topic. I hope you remember in physics, when we discuss speed, we actually are discussing the distance covered by a specific object or vehicle over a specific amount of time. So what we are doing is that we sometimes define speed as a rate of traveling or rate of covering distance per unit time. So we do use the word rate in physics as well. Now let me explain, whenever I use the word rate, whether that happens in physics or that happens in chemistry, basically what we are trying to say is that we are dividing something with respect to time. That's what the word rate in science means. So as soon as I use the word rate, remember there would be a fraction, and in that fraction, the denominator is going to be time. It's as simple as that. Since this is a speed of reaction, so what we are going to talk about is the progress of reaction, how speedy the reactants are converted into products. So it's pretty easy to say that the amount of reactants would decrease or the amount of products would increase. And we are actually taking that per unit time. It may be per second calculation, it may be per minute calculation, it may be per hour calculation. That depends on how fast or how slow the reaction is going. So we are basically talking about a change in concentration or amount of reactants or products per unit time. And that's the best way to define it. Now, that's just the definition. On upcoming pages, we're going to design experiments, entire experiments, to find out that how the change in concentration would be measured, or maybe volume, as says in the formula, or maybe mass, and how we are going to calculate it over time. So let's go on. And let's further elaborate this definition, since this definition definitely requires an activity. So moving on to activity number 5. This is actually the first activity of this chapter. However, fifth activity for the unit. That's why it's numbered as activity number 5. All right, a quick safety note. We are also supposed to wear eye protection and avoid skin contact as long as we're dealing with acids. So this is an investigation in which we require the rate of reaction between marble chips and hydrochloric acid. Now, as we already know that marble chips are actually made out of calcium carbonate, and since this is a carbonate salt, it contains CO3, and from the previous unit, we know as soon as it is going to react with an acid, it is going to produce water, it is going to produce carbon dioxide gas as well. Now, carbon dioxide gas in this reaction, when produced, is produced in the form of bubbles. We may also call it effervescence. Now, in this case, what we do is that we do this experiment in such a way that we call it loss in mass experiment. All right. I'm giving this name for a very specific reason, which you're about to see in the diagram in front of you. Loss in mass, which means mass would be decreased. Now, since you know, for any given chemical reaction like this one stated over here, the mass remains conserved, which means the mass of reactants on your left, which are calcium carbonate and hydrochloric acid, should be equal to the mass of products on your right. And the products in this case is a salt, calcium chloride, water, in carbon dioxide. We do understand both masses are supposed to be same. So there would be no increase in mass, there would be no decrease in mass, mass should remain the same. However, if in any experiment there is a gas being produced as a part of product, and we allow the gas to pass out of the system, like in this case, take a look. We have marble chips, we have cotton wool, we have dilute hydrochloric acid, and before reaction, their mass is measured. And after the reaction, when we have used this dilute hydrochloric acid on marble chips, we have a cotton wool so that there is no splashing of acid outside and we can keep ourselves safe. But there would be some bubbles of carbon dioxide. And since there is some space in cotton, the carbon dioxide should be able to move out of the system. Although carbon dioxide is a gas, but that gas definitely has some mass. And since the gas leaves the system, there would be a decrease in mass, which is shown in this diagram with a negative mass sign. I hope that makes sense, right?
Yes.
Great. If it does, let's go with the details of the reaction. So the following procedure is used. We use the measuring cylinder and measure 25 cubic centimeter of 2 mole per decimeter cube dilute hydrochloric acid. We only take 5 grams of large marble chips in a conical flask. We place a piece of cotton at the opening of the flask. It's just there so that it allows the carbon dioxide gas to escape the reaction, but it would stop any acid spitting out. It would keep us safe. The marble is in excess. Some of it would be left over even when the acid is all used up. Place everything on the balance, reset it to 0. Add the acid to the marble chips, record the reading on the balance after every 30 seconds, and make sure you consume all of the acid since the marble is in excess, so you're supposed to use all of the acid. Now in part B, where there was some negative mass on the balance, you would know what would happen during the reaction. The acid has been poured into the flask, everything has been replaced in the balance. Once the reaction starts, the balance show a negative mass. The mass goes down because the carbon dioxide escapes through the cotton wool. Now, what we do is that since we're getting our readings after equal time intervals, which was 30 seconds, we are going to plot a graph. We're going to plot a graph of a mass of carbon dioxide lost against time. The steeper the slope or the gradient of the line, the faster the reaction. I'm going to explain this line on the graph since this requires a little bit of explanation. Now, let's go to the figure and see how much mass has been produced in carbon dioxide or there has been some loss. Let's go through this diagram first. On your x-axis, you would find time in minutes. On your y-axis, you would find mass of carbon dioxide produced per gram. Now, the graph is very steep at the start, and you would notice that the graph is rising almost all up. We call it a steep graph. Remember, the closer the graph is to the y-axis, the steeper is the graph. The farther the graph is from y-axis, the less steep the graph is. That's the way we define it. And that's the way you'll find the words written along with the description of this diagram. So since this line is pretty close to y-axis, we call this a steep graph. It is showing lots of carbon dioxide is produced in the very first few minutes of the reaction. The reaction is fastest at start. The graph is getting less steep, showing that the reaction is slowly slowing down as soon as we proceed. Take a look, the reaction is pretty fast in the first 2 minutes. Moving on to the next 2 minutes, the reaction becomes slower. Next 2 minutes, it becomes further slow. Next 2 minutes, it becomes more and more slow. So you would notice that there would be very small amounts of carbon dioxide produced during these times. You will notice these circles are getting smaller, which means at the start of this reaction, it was producing a lot of carbon dioxide, and it slowly went down, producing lesser and lesser amount of carbon dioxide as the graph proceeded. So the graph is getting less steep, showing that the reaction is slowing down. Graph becomes almost horizontal, so showing no more carbon dioxide is being produced, and the reaction has almost stopped. Or the reaction has stopped at a flat line. We also call it a flat graph. tangent drawn at the 5th minute, and gradient of this tangent tells you that the rate of reaction at this particular time point, it's almost 0. So flat means nothing is being produced, right? Okay, how do we find tangent of the graph? We have these lines. Let me clear mine up. You would see a tangent at these lines. We commonly draw tangents in maths, and I hope you have studied that in maths. Did you?
Yeah.
Okay, so you would know that we draw a tangent, and sometimes we take points from the tangent, and for these points help us to measure the values of x-axis and y-axis, and we can put them in a formula over here, and it's pretty easy. Divide the values of y-axis with the x-axis, and you can get your answers. We are calling it a tangent in terms of mathematics, but since that is something we're going to call rate, it's pretty simple that the value of tangent, that the value that we are actually calculating in terms of tangent is rate. So what is rate? Rate is y-axis values, mass of CO2 lost over time, which is x-axis values. So this is pretty simple. We can notice it for different values. For example, the average rate of reaction in the first minute. This means we take it like this all the way to over here. Since this is 0.47, since this is 1, so we divide these values like this. What if you need to find the value in the second minute? Let's move on. Since this is pretty simple, we get the values of grams of mass of carbon dioxide produced per minute of time. I hope this is understandable, is it?
Yes.
Good, great. Let's go with other pieces of time, since that is going to be a little bit of different calculation. Okay, let me, in fact, why don't we zoom it out? This would help us see all the values in the graph at the same time. All right. And the average rate of reaction in the second minute. Now we need to calculate the values only for second minute. Since we are talking about second minute, so we need to do it like this. I'm trying my best to draw straight lines, and hopefully I'm successful. No, not this time. Okay, so for the second minute, we need to take the values in such a way that we need to divide the second minute value with the first minute value, and we divide the second minute value of x-axis, and these are the values for y-axis, y and y, with the first minute value of x and x. All right, so actually we do it like this. In maths, we usually call this tangent as y2 minus y1 over x2 minus x1, which means the second value of x and the first value of x, the second value of y and the first value of y. I guess they are taking this one as 0.67, this one as 0.47, this one as 2, and this one as 1. So this gives you 0.2 answer, and this gives you over 1, right? So that's how we get this value. Make sense?
Yes.
But if we find the average rate over first 2 minutes, that would be 0.67, this value and this value. So you'll get this answer, right? Whichever one you compare, you would notice that every time you jump from first minute to second, second minute to third, third minute to fourth, you would find out that the value, the rate is decreasing, which is pretty much giving us the notion that the reaction is slowing down. It was fastest at the start, and it's gradually slowing down. Make sense?
Yeah.
Great. So you should be able to calculate the values for any graph given in the questions for any number of minutes that they ask you from the graph. And hopefully that's easy after this explanation. Is it?
Yeah.
Good, good. Now we can see the reaction is fastest at the beginning. It slows down and eventually stops because why? Here comes the reason. All of the hydrochloric acid has been used up. This must be a question. Students usually come up with this question that why is the reaction slowing down? It's pretty simple. The reactants are being used up. The reaction slows down because you are using the reactants. And I sometimes come up with a very simple example. Sometimes we give homeworks to students. When they start the homework, they're all motivated and energized. When they're done with half of the homework, their energy goes down, so does the motivation, and sometimes some students tend to slow down. Why? Because they have consumed up that motivation and that energy of doing the homework. And this may come true for any of the tasks in life. At the start of any task, we are very much motivated, we are very much energized, but at the center or about the end of the task, we are actually really tired. We have used up all of our motivation and energy, so we get tired and we become slow, right?
Yeah.
So the same thing happens in the reactions. We can measure how fast the reaction is going at any point by finding the slope or the gradient, just like I shown you the method. And this is the rate of the reaction at that point rather than the average. So if you need to find the gradient and not the average, that means you're doing it at a specific amount of time, at a very specified time. So you draw a tangent to the line and you find its slope. For example, exactly at 5 minutes, the carbon dioxide being lost at the rate of about 0.05 grams per minute. And for that, you need to understand about this tangent drawn over here. I hope you understand how to draw a tangent and calculate the value. Do you?
Yes.
Okay. It's pretty simple. Let me go through that again, just to be on the safe side and just so that we are both on the same page. Since we are talking about 5 minutes, to take a line to 5 minutes and you know where to draw the straight line. Or try drawing the straight line exactly at this point where we have this 5 minutes. You can do it like this. And these are the values for x2 and x1. These are the values for y2 and y1. I think it's pretty easy that your answer would be equal to y2 minus y1 over x2 minus x1, and you'll get your answer. This would be around 0.05. This is what has been done to calculate this value. All right, I hope that makes sense. And I hope you are doing the same process. Are you?
Yeah.
Good, good. So I'm going to clear it up and we're going to move forward. All right. You can follow this rate of reaction by measuring the volume of carbon dioxide given off. Now, we are coming up with another method of doing the same experiment. So it's not just the loss in mass experiment that we need to do. That was just the first kind of experiment that we usually design for finding out the rate of a reaction. Now, the second kind of reaction is volume of gas collected. In this method, we tend not to lose the gas to the environment. Instead, what we do is that we collect the gas. And it's pretty simple. This time, we airtight the flask with the help of a cork or anything that can turn the flask airtight so that nothing leaks out of the system. We can connect it with the help of a delivery tube to a gas syringe. A gas syringe is just like a normal syringe. And as soon as it would produce the gas would go over here. It would move the plunger all the way outwards. The plunger would move outwards and will have the gas filled. And we have the measurements or readings over here, graduations, and you would know how much of the gas have you collected. You can also do it or a delivery over water. Take a delivery tube, pass it through a trough of water. This is a trough, which is not mentioned over here since everything else is mentioned. We put a measuring cylinder in an inverted way and we collect the carbon dioxide gas over here. But let me tell you, this is a less accurate method and this is a more accurate method. So always prefer collecting the gas in a gas syringe rather than a measuring cylinder. Make sense?
Yes.
Great. So this is the second kind of method. And we can easily find out the volume of gas collected in this experiment. Since whatever we are using is volume, we cannot draw a graph of mass in this case. We need to first draw a graph of volume, then we can later on turn it with the help of calculations into mass, and then we can draw a graph of mass as well. But first, as far as the actual readings from the system or from this experiment activity is concerned, you're supposed to draw a graph of volume collected. Okay. So remember, the marble chips were in excess. There was more than enough to react with all of the hydrochloric acid. So there will always be some unreacted marble chips in the flask at the end of the experiment, whether it's volume of gas collected or whether it's loss in mass. This is pretty easy to understand, since it's just a reminder. Okay, now let's talk about a theory. We call it collision theory. Before I move on with collision theory over here, I'd like to explain collision theory on my own, since it's going to give you a very good idea. Now, in collision theory, we're going to discuss about a few points. Number one, molecules or particles move and collide with one another. All right. In most of the cases, in most of the experiments, what happens, the particles, they may be molecules, they may be ions, they may be atoms, they can be anything. I've just used this simple word for molecules. It does not necessarily have to be a molecule, all right? So the particles move and collide with one another, all right? Number two, collisions are of two kinds or two types, right? First type, successful collision. What is the successful collision? I'm going to draw it. A reactant molecule comes closer to another reactant molecule, so much so that both reactant molecules collide with one another with some force, and then they return back as product molecules if their energy is greater than or equal to activation energy. We're going to divide activation energy. It's the minimum amount of energy which the particles are supposed to have, so that when they collide, they are converted into products, right? And I'm going to write point number 4 over here, which is the second type, of course. And as you might have guessed, it is unsuccessful collisions. Unsuccessful collisions are funny. Reactants come close, and these particles collide with one another. They really tend to fight with one another like that, but they return back in the form of reactant particles. They are not converted into products. Why? Because their energy was less than activation energy. Not even equal, not even greater, less than activation energy. All right? Okay, let me explain with an actual example. Do you use any gas to cook food at home? Or are you doing it with the help of electricity?
Electricity.
Okay, in many parts of the world, they are using natural gas, methane, propane, butane. They are using cylinder gases filled up in cylinders, and they use a gas and they burn the gas to actually produce some energy and cook food out of it. All right. So we also do it with cars. We are burning petrol or gasoline in cars, and we are producing energy to run cars. Let's talk about that. Let's suppose on one end we have a petrol molecule, a gasoline molecule, fuel for car. And on the other hand, we have an oxygen molecule. Now, the petrol in the air, if collides with oxygen, returns as petrol and fuel and oxygen. Nothing happens. Literally, nothing happens. We call it an unsuccessful collision. Petrol and oxygen can be present in the air and still not burn, still not be converted into what fuels are actually used for. But sometimes the fuel particle comes closer to the oxygen molecule and returns as carbon dioxide and water. Why? Because we might have introduced a flame over here, or we might have introduced a spark over here. In cars, we usually have the sparking system. We have the batteries in cars which produce a small spark. That spark is good enough to burn the fuel, ignite the fuel burns, it produces energy, and we run the car. So I hope you understand this flame or this spark, the small flame is actually producing it or giving it the activation energy, the minimum amount of energy that we need for a reaction, for a collision to be successful, and the reactants to be converted into products. I hope that makes sense now. Right? Does it?
Yeah.
Good. So we sometimes provide with a necessary energy, the minimum energy for which we can jumpstart the reaction, for which we can convert the reactants into products. That kind of energy is known as activation energy. If we are successful with the reaction and reactants are converted into products, we call those collisions successful collisions, those reactions as successful reactions. And if we don't have enough amount of energy, the particles are simply going to collide with one another and return in the form of particles themselves, and nothing happens. We call those kind of collisions as unsuccessful collisions. This is collision theory. All right. Let's go with further examples. Now, every reaction can be discussed in terms of activation energy, successful or unsuccessful collisions, or simply in terms of collisions. The reactions we just discussed, marble chip, let's consider this one as a marble chip, and there are a lot of acid molecules and particles for collision. So they come to the surface of marble chip, they collide with them. Some of them are actually successful, some of them are actually not. For most of them, this reaction is pretty fast. For most of them, they are successful. So what happens is that in the start of the reaction, there are a lot of acid molecules, as you can see in that diagram. This is the very early part of the reaction. We have enough acid, and a lot of acid particles try to collide, try to attack the marble chip at the same time. So the rate was higher, and there was much amount of carbon dioxide produced in the start of the reaction. Later on, almost near to the end of the reaction, there would very less amount of particles of acid left. So there were, since very fewer particles, there were very few attacks on the marble chip, and the rate of reaction was slower, and the graph became flat since we were producing very less amount of carbon dioxide. Make sense?
Yes.
Okay. Now you need to understand that in the previous chapters, you do understand acids basically have hydrogen ions, H positive ions, and a reaction occurs because H positive ions collide with the carbonate ions and they produce water and carbon dioxide. So you should understand these red particles are not the entire acid molecules. These are the H positive parts. And this marble chip has a CO3 negative 2 parts, and both of these parts react to form water plus carbon dioxide, which were only the two products of the reaction. Since the reaction was also producing a salt, there was a third product, But for that third product, the negative part of the acid and the positive part of the marble chip were involved. That's why these two were reacting to produce the salt, right? Make sense?
Yes.
Great. Let's move on. This was the very basic of this chapter. If you understand these basic parts, the rest of the chapter is for the types of graphs and types of reactions that we're going to understand for rate of reaction. So it's further elaboration. If you understand the basics, the elaborations are going to come easy to you. Now, a different form of a graph. What if we change the graph? What if we don't talk about the product or formation of product or mass of product or volume of product? We don't talk about the product at all. What if we talk about the fall in the concentration of the reactant, right? What if we do that? Let's say we were talking about the concentration of dilute hydrochloric acid. So on x-axis, we put the time in minutes. On the y-axis, instead of producing the mass or volume of carbon dioxide gas, we put up concentration of acid, which is actually a reactant in mole per decimeter cube. This time, instead of having an increasing graph, we have a decreasing graph. So let's make some sense out of it. If we have a product over here and time over here, the graph would be like this. And if we have time over here and we have a graph of a reactant over here, let me clarify, the graph would be like this. All right, let me redraw this line since my drawing sets are a little poor. All right, I hope this now makes sense, right?
Yeah.
So for reactants, we usually start from the top. Why? Because the concentration of the reactant is maximum at the start of the reaction, but it falls really quickly. Since we're consuming the acid, so the concentration goes less and less while the reaction slows down. And at the end of the reaction, since all of this reactant has been used up, the reaction stops. And actually, the reaction has to stop since the one reactant has been completely consumed up. In this case, the acid. Right?
Yeah.
Great. So these are the three parts of the same graph, but the graph is somewhat different since we're not taking the product at y-axis, we're taking the reactant at y-axis. So we always like to call it that the product has an increasing graph and the reactant has a decreasing graph trend. In both the cases, you would notice that the graph is called steeper at start since it's closer to the y-axis, and when it's farther from the y-axis, it is known as less steep. So the definition of steep is pretty much the same whether we are talking about the product or we're talking about the reactant. Make sense?
Yeah.
Great. Now, let's clear it up. Let's move forward. Now, let's talk about a few factors that can change the rate of reaction for us. This is the first factor that we are going to begin with. Surface area of reactants. If you change the surface area of reactants, does the rate of reaction or speed of reaction changes? Whether the reaction becomes faster or the reaction becomes slower, we have an entire activity number 6 to prove that. So in this practical, we're going to investigate the effect of changing the surface area. We're still going to consider the same marble chips, going to study the same rate of reaction, and with the same reactant, dilute hydrochloric acid. So actually, the safety notes and the rest of the stuff remains the same. Moving on. We are going to repeat the reaction in different ways. First of all, we went with original marble chips, which were actually large pieces. And then we performed another experiment with some smaller chips, right? So you would notice that the large pieces has this graph. These are for large pieces. And you would notice this is a graph for small pieces. The things to note down over here is that you have a much steeper slope in start at the beginning of the reaction with smaller pieces. both the graphs become horizontal. Both the graphs have to, at the end, become flat. But with the small pieces, since the graph is steeper at the start, it becomes flat quickly. So the reaction is faster. The rate of reaction is higher for smaller pieces, all right? And the rate is somewhat slower for larger pieces, and it takes some time before it becomes flat. Make sense?
Yeah.
Okay, let's elaborate it a little further. And this time I am going to talk about particle size. I'm going to further elaborate it. Surface area. And I'm going to relate it with rate of reaction. Now, when we were using large pieces, so basically the particle size is large. That's why I'm using this word. The surface area was small, right? And the rate
Yeah.
of reaction was slower, right? Then we did another experiment with small pieces. And this time we had a bigger surface area. Let's call it smaller. And the rate of reaction was somewhat faster. Do we have another option? Yes, we do. We can go with powdered. And I hope you understand that powdered is the most form with the smallest particle size, but definitely it would have the biggest surface area. And fastest would be the reaction. Let's explain it. Let's explain it with something, with some example that you might not have observed, but you did went through that when you were a child. Okay, Bashar, tell me, do you like candy?
Yeah.
Yeah, everyone likes candy, right? If they don't like it at this age, at my age, of course, they definitely like it when they were children. When they were toddlers, they used to love candy. They would do anything for a candy, right? Now, you
Yeah.
might have noticed something with a candy. As soon as you unwrap a piece of candy and you put that big candy in your mouth, and if you don't chew it up, you have a large piece, the surface area is smaller, it would dissolve slowly, and you could actually enjoy the candy for a few minutes. But since we're children at that time and we don't know, we are very hasty and impatient. What do? We start chewing that candy and we break it down into smaller pieces. Now the surface area becomes bigger, the reaction becomes faster, and we actually can enjoy the candy for hardly a minute. And if we are very impatient, somebody like me, they would quickly chew the candy, turn it into powder. The surface area becomes the biggest. Your mouth dissolves it in a matter of a few seconds. And in less than 10 to 20 seconds, the entire candy would dissolve, and you would notice that you weren't even able to enjoy it for a good duration of time. And those are the impatient kids who ask the parents for another candy. Can I get another one? And you might have done it in 1.2. Do you remember that from your childhood?
Yeah.
Do you still do it?
Yeah.
Everyone does it. Everyone is impatient when it comes to candies. Even I am at this age. So now with this kind of example, you would easily understand how particle size relates to surface area and how it changes the rate of reaction. Now you would notice that surface area and rate of reaction are somewhat directly proportional. In such a way, if surface area is smaller, the rate of reaction is slower. And when the surface area is biggest, the rate of reaction was fastest. But in case of particle size and surface area, you would notice that they are not directly proportional. They're actually inverse to one another. When the particle size was large, the surface area was slow. If the particle size is very small, the rate of reaction becomes very fast. So actually, they are inverse to one another. They're inversely proportional. Make sense?
Yeah.
Great. Can I erase it all? Can I move forward?
Yes.
Good, good. And by the way, I like your honesty about still doing the same stuff with candies. All right. So the reactions between solids and liquids or solids and gases are faster if the solids are present as lots of small pieces rather than few big ones. And this is the diagram where they explain it. Now you would have an idea how a big piece has actually a smaller surface area and it gives a slow reaction, while smaller pieces have a larger surface area and they can actually turn up the reaction pretty fast. And with powdered, imagine we have these particles separate and we have so fast of a reaction that the reaction would occur in a matter of seconds. So that's why when the surface area is greatest, the reactions are fastest. Why? We use a specific term for that, and this term is going to be really helpful to express yourself as in exams. When the surface area is greater, there are more particles exposed on the surface, so we use the word frequency of successful collision increases. Frequency means the number of successful collision increases. So here, these particles may have lesser number of successful collisions, but here they would definitely have a higher number of successful collisions. So we call it a higher frequency of successful collisions. Higher number, higher frequency, both words are good to go, and both words would get you the marks in exams, right?
Yeah.
Why is that so? These particles will not be exposed to acid particles since they are surrounded by other particles. That's why this one's slow. And that's why these ones are fastest. And that's why the one with powder, which aren't even mentioned over here, would be the fastest in that case. Since those cases have been discussed in past paper exams, so I discussed this case along with these two over here. If that all makes sense, let's move on to the next page, shall we?
Yeah.
Great. Okay, so the larger surface area is frequently used to speed up reactions outside the lab. For example, sorry, my internet connection was a little static. Okay, I was saying larger surface areas are frequently used to speed up the reactions outside the lab. For example, a catalytic converter for a car uses expensive metals such as platinum, palladium, or rhodium, and they are coated onto a honeycomb structure, just like the honeybee's comb structure, uh, onto a very thin layer to give the maximum possible surface area, which we can see over here. It's actually a hexagonal structure like this. That's why we call it a honeycomb structure, like this, something like this, right? Okay. In the presence of these metals, harmful substances such as carbon monoxide and nitrogen oxides are converted into less harmful substances such as carbon dioxide and nitrogen. Since carbon dioxide and nitrogen are present in the air all the time, so they are considered less harmful than carbon monoxide, the formula for which is CO. And let me tell you, CO is toxic. It's not good for humans. Nitrogen oxides, which are NO. NO2 is also a nitrogen oxide, and they're not good for humans either because they are causing a global warming and rapid temperature changes around the planet, all those problems of pollution and environment. So the larger surface area means the reaction is very rapid. This is important so that we can convert the harmful substances into the less harmful ones. Because the gases in the exhaust system are in contact with catalytic converter for a very short time, so we need the reaction to be extremely rapid and we need to get rid of these harmful substances. Make sense?
Yeah.
Okay, these paragraphs may seem pretty uh, unimportant, but they have been considered in past paper exams. So make sure this becomes a part for memorization for you. So try memorizing these pieces of information. All right.
Okay.
Great. Let's clear it up, move forward to our next part. And this is the second factor. And by changing this factor, we can definitely speed up or slow down a rate of reaction. This is changing the concentration of reactants. Now, what is the effect of changing the concentration of reactants? Let's do the same experiment, but this time change the concentration of hydrochloric acid. Now you would notice that they have taken two different acids and we have two different lines for them. The original concentration, which I guess was 2 mole per decimeter cube, with a blue line, of course, having a faster rate of reaction, a steeper curve, and half the concentration, which would be 1 mole per decimeter cube. And you would notice that there would have less slow rate of reaction. So change the concentration, and you would notice that it changes the steepness of the graph and it turns in a slow reaction, right? Remember, a reminder over here tells us that the marble chips were in excess, so this makes no difference. So in the second experiment, since we started off with half the concentration, so we have the graph ending up at half the line. So you would notice this point and this point are exactly half of one another. Also, these distances almost the same as well. I hope that makes sense, right?
Yeah.
Okay, now, since we are using 25 cubic centimeter of 2 mole per decimeter cube on the blue line experiment, and we're using 25 cubic centimeter of 1 mole per decimeter cube hydrochloric acid, and the lines are ending at different points, which means half as many moles of carbon dioxide would be produced for this red experiment than this one. Let's suppose we're producing 2 moles of carbon dioxide over here, supposedly, and we'll only produce 1 mole of carbon dioxide over here. All right? I'm just stating number of moles, although the mass is given over here, which is entirely differently. That's why I'm just supposing the values. We can definitely count the exact moles of carbon dioxide from these masses, right? The formula is pretty simple, mass over molar mass, for which the carbon dioxide is 44, divide the values, you'll get your answers. But that's not the point over here. The point is, if you increase the concentration of the reactants, the reaction becomes faster. Increasing the concentration actually increases the number of acid particles in a fixed volume. Therefore, the particles are closer together, collide more frequently. There are more chances of successful collisions. Of course, there would be more successful collisions as well. And the particles would hit one another to be converted into products more often. Frequency of successful collision increases, and hence the rate of reaction increases too. And the same lines are written over here. The particles collide more frequently, or there are more collisions per second of time. Make sense?
Yes.
These lines and these words are written over here so that you can use exactly these words or these lines instead of using your own words. Sometimes we don't use good enough of a terminology, so using these words would be a very good idea. All right? So moving on. Another activity. Investigating the effect of changing the concentration of the acid on the rate of reaction between marble chips and dilute hydrochloric acid. Okay. Now, we are going to change the concentration of the acid, and we are going to do the experiment a little differently than what we have previously described. Now, we can repeat our previous experiment in activity 5 using original large marble chips, but using hydrochloric acid of different concentrations. Everything else would be the same. The mass of marble chips is 5 grams. Total volume of acid is 25 grams, 25 cubic centimeter, my bad. And we can dilute the acid by adding distilled water to original 2 mole per decimeter cube solution, but making sure the total volume of water and acid remains at 25 cubic centimeter. So what do? We take half the amount of original HCl and we mix it with half of the amount of distilled water to get the original amount of 25 cubic centimeter. All right.
Okay.
So when they're half and half, we would actually half the concentration. If only 5 cubic centimeter of original HCl is mixed with 20 cubic centimeter of distilled water, the acid is now 1/5 of the original concentration, which is 0.40. 1/5 means that you're going to multiply this 1/5 into 2, and the answer would be 0.4. So 2 mole per decimeter cube is now converted into 0.4 mole per decimeter cube, and that's why it's written over here. Why? Because we took 1/5 of the volume of original acid and mixed with 4-5 volumes of water. Make sense?
Yes.
To better understand it, they have also written the formula of concentration, which we have used in Unit 1 in moles chapter. So moving on, in this experiment, we're going to calculate the average rate during the first 30 seconds and the mass of carbon dioxide lost in first 30 seconds. We're going to go with a loss in mass experiment. We can calculate the average rate within the first 30 seconds by dividing the mass loss by 30 seconds over the time, which is of course 30 seconds itself. So that is 0.32 grams mass loss over 30 seconds. So the answer is 0.011 grams per second. To identify the effect of changing concentration rate, we plot the results for different concentrations on a piece of graph paper with rate on the y-axis and concentration on the x-axis. Now, this is a little bit of a different graph. We're not putting up the amount of reactant on the y-axis or amount of product on the y-axis. Instead, what we're doing is that we're taking concentration of the acid on x-axis and rate on directly on y-axis. And you would see we get a straight line. What are they trying to prove? They are trying to prove from this straight line that these two things are directly proportional. So if the concentration doubles, the rate doubles. If the concentration triples, the rate triples. That's what they are trying to prove in this kind of graph. So remember, concentration of reactant and rate of reaction graphs are straight lines like these. They start from origin and go all the way straight in such a way that every time you plot a point, you'll get an exact square, like this, right? Which would give you the idea when the concentration increases, the rate increases too, and almost directly proportionally, right?
Yes.
Okay. As much simple as it seems, it actually isn't that simple. Let's first explain a few words before I explain the unsimplicity of this part. Now, the words proportional and directly proportional mean the same thing. If the graph was plotted was a straight line and that did not go through origin, this is not a proportional relationship. In this case, we would describe the relationship as linear since this starts with origin. So we call it a proportional relationship. If the graph was like this and there was this part missing, we'll call it linear. And this graph, since it touches the origin, it's proportional. By origin, I mean both the values start from 0 and 0. Make sense? But that's just more mathematics than it is chemistry. What I was trying to say is that this graph is a straight line. Straight line means simple. When the rate, the concentration of the reactant increases, the rate increases as well. Double the concentration, double would be the rate, triple the concentration, triple would be the rate, so on and so forth, right? But this relationship isn't as simple or as uncomplicated as it seems. In some reactions, the rate of reaction is proportional to the concentration of the reactants to a particular aspect. We call those first order reactions. When you go to higher levels, you would understand that sometimes increasing the concentration of one reactant has no effect on the reaction whatsoever. So they have a different order of reaction. But that is a part of A levels. So we are not going to go with the details of this, all right? Since I haven't seen a question about these details in any of your past papers either. Okay, so I'm simply going to move on to the next factor, which is changing the temperature of the reaction. Before I start with a new one, do you have the questions from the previous one? I forgot to ask.
No.
Okay. So let's move on to temperature. What effect does the temperature have on a reaction? We can do the original experiment again, but this time at a higher temperature. So reactions would get faster as the temperature increased, the graph becomes steeper and finishes sooner. The same mass of gas is given off because we have used the same quantities of everything in the mixture. So original temperature has a less steep graph, higher temperature, more steep. The higher would be the temperature, the steeper would be the graph. So why is higher temperature graphs more steeper? There are two factors that we need to explain over here. Now, the first factor, increasing the temperature means the particles will get the energy to move faster, which means they would collide more frequently, which means the reaction rate would go faster, but that's account for only a small part of increase in the rate. Now, we need to also understand one more factor, which is more important than this one. For an order of a collision to cause a reaction, a successful collision actually, we have said that the particles need to collide with a minimum amount of energy, and we have been calling the term activation energy. A relatively small increase in temperature produces a very large increase in number of particles with energy greater than or equal to activation energy. So what happens? Increasing the temperature basically gives particles energy greater than or equal to activation energy. What does this mean? This means more number of particles would have energy greater than or equal to activation energy, which means when those particles would collide, they would turn out to be successful collisions, increasing the rate of reactions. Take a look, low temperature, just these particles are having successful collisions because only they have the energy equal to or greater than activation energy. At higher temperature, more collisions will have the same effect and will have an energy equal to or greater than activation energy. So there are higher number of successful collisions. So increasing the temperature actually doesn't just make the particles go fast. It gives the particles energy that should be greater than or equal to activation energy, giving them a chance at a successful collision and being converted into products, increasing the rate of the reaction. Make sense?
Yes.
A key point, as an approximation, a 10-degree increase in temperature approximately doubles the rate of reaction. This works for quite a number of reactions that we meet in the lab, right? As long as the temperature remains within a few tens of degrees of room temperature, few tens of degrees, room temperature is 25, so increase it to 35, increase it to 45, increase it to 65, 55, it would work. That doesn't mean if you increase it to 1000, it would work in the same way. No, just a few tens, like these. The rate of reaction would double at every step. After 100 degrees centigrade, we won't see that much of good increase. Make sense?
Yes.
So this has a limit. Although temperature does bring a difference, but this has a limit. For different reaction, there are different limits. And what are the limits? We usually don't do it at this level. We keep it simple at this level. And I think this is good enough for here. Now, we have a couple of more factors left. Moving on to the last of factors, I think the second last of the factors, pressure of the reaction, changing the pressure on the reaction. Changing the pressure on the reaction, and actually this does not bring a difference to solids or liquids, but this would bring a great difference to gases, does speed up the reaction. So if we are doing if our reactants are gases, this would bring a difference. If our reactants are solids or liquid, there would be almost no difference changing the pressure. So if we have a fixed mass of gas, we can increase the pressure by squeezing it into a smaller volume. Now, if you remember from the very first chapters, the gas particles are very far away from one another. Squeezing it a little bit can force those particles into a smaller volume. We say that this has less pressure and this one has a higher pressure. The one that has less pressure has a high volume, and the one that has high pressure has less volume. So automatically you'd get an idea that in this case, the collisions, there are less chances for collisions. But if you squeeze them in a smaller volume, they would have more chances at collisions, which automatically gives the idea that when the particles are closer together, they would collide more frequently. And this is exactly the same as increasing the concentration of a gas, right? Make
Yeah.
sense? In solids and
Yes.
liquids, the particles are packed closely together. There is hardly any space between them, so changing the pressure would not change any uh, effect on the rate of reaction or anything like that. So this is the same diagram I drew previously. So that was, I guess, the second last factor. Moving on to the last of factors, I guess there is just catalyst and light left. I don't know whether light is a part of this chapter or not. Let's move on to catalysts. Catalysts are substances that speed up chemical reactions. Good part, they're not used up in the process. They're still there, chemically unchanged by the end of the reaction. This is the entire definition. Sometimes the student write this part of the definition and leave this part out of it. I was saying sometimes they leave the second line out of it. That's not correct. It's better to write from here to here because that's the whole definition. They aren't used up in the process, they're still there. How? They are not chemically unchanged. They might get physically changed, right? We might change them physically. It may happen that we, at the start of an experiment, add a solid catalyst and it is converted into a liquid at the end of an experiment. This is a physical change. This may happen. But chemically, it won't change. It would remain the same chemical and the identity won't change. It can't be that we used water as a catalyst and it turns into carbon dioxide by the end of the reaction. That cannot happen. So the catalysts do not change chemically at the end of the reaction, but they might change physically, right? They're unconsumed. Small amounts of catalysts can be used for process lots and lots of reactant particles. I'm going to come up with an example, and this is going to become easier for you after the example, that how can a small amount of catalyst can go for a very big reaction. Bombardier beetles defend themselves by spraying a hot, unpleasant liquid at their attackers, as shown in the diagram. Part of this reaction involves splitting hydrogen peroxide into water and oxygen using the enzyme catalase. Enzymes are biological catalysts. You might have already studied them in biology if you're opting for it. These reaction happens almost explosively, produces a lot of heat. The same enzyme can be found in potatoes or even liver tissues. There are a lot of other things that also catalyze the decomposition of hydrogen peroxide. For example, in labs, we use manganese 4 oxide. It is also known as manganese dioxide. The formula is MnO2. We may also use lead 4 oxide, the formula for which is PbO2. Manganese 4 oxide is what is normally used in the lab for decomposition of hydrogen peroxide, the formula for which is H2O2. It decomposes into water and oxygen. Notice that we do not write catalyst into the equation because they are chemically unchanged at the end of the reaction. If you want, you can write their name on the top of the arrow. For example, we can write MnO2 right on top of the arrow. You may write the name, you may write the formula, it's entirely up to you. If anything is written over here on top of the arrow, you can automatically assume that this one is a catalyst. Why are we writing on the top of the arrow? Because it's not a reactant, it won't get consumed in the reaction, it's not a product, it won't get produced in the reaction, it is just there to speed up the entire reaction. Showing that a substance is a catalyst, how do we keep saying for the fact that it is not used in the reaction, it is not consumed up? Can we prove it? Yes, we can. Now, it isn't difficult to show that manganese 4 oxide speeds up the decomposition of hydrogen peroxide to produce oxygen. We have two beakers. One contains hydrogen peroxide solution On the right hand, we have added a little amount of black solid, MnO2, to speed up the reaction. Notice, as soon as we add it, it produces a lot of water and oxygen, which we can see in the diagram as well. But how can you show that MnO2 is chemically unchanged by the end of the reaction and it hasn't been used up? We can easily separate it from the liquid. How? Filter it. Weigh a filter paper. Allow the paper and residue to dry. Reweight it, and you can actually calculate the mass of remaining manganese peroxide. You would find that the mass does not change. So the mass we added over here and the mass that we filtered out of this part and we reweighted will have no change in them, proving MnO2 was never consumed in the reaction. Make sense? Right?
Yes.
Good. So let's go for an activity. Let's investigate the effect of different solids on catalytic decomposition of hydrogen peroxide solution. We are going to measure the volume of oxygen produced. Since this reaction produces a gas, it's pretty easy to trap the gas in a gas syringe and finalize that whether how much oxygen is produced in the reaction. So it's pretty simple. You have a flask, you have hydrogen peroxide solution, you have manganese ore powder added to it. It would produce oxygen. Oxygen would push this plunger of the syringe out. And then we can use a string hydrogen peroxide solution, a weighing bottle containing manganese peroxide, and we can then reperform the experiment. The following procedure can be used: that we measure 100 cubic centimeter of 2 volume hydrogen peroxide and transfer it to 250 cubic centimeter conical flask. Now, when I use the word 2 volume, let's clarify. Volume, meaning volume, is a measurement of concentration for hydrogen peroxide. 1 cubic centimeter of 2 volume hydrogen peroxide solution decomposes completely to give 2 cubic centimeter of oxygen. So if we're talking about 2 volume, every cubic centimeter of it would give out 2 cubic centimeter of oxygen. All right. So weigh out 0.20 grams of manganese peroxide on a balance and the manganese peroxide to hydrogen peroxide and quickly replace the bung with the gas syringe already attached. Swirl the reaction mixture at a constant speed. Recover the amount of oxygen produced every 20 seconds for up to 3 minutes. Plot the graph, volume of oxygen versus time on x-axis, volume of oxygen on y-axis. Repeat the reaction with 0.20 grams of lead and copper oxide, but keep everything else the same. You would find 3 lines: copper oxide at bottom with a green line, lead oxide, it's actually lead 4 oxide, PbO2, with a line almost closer to the x-axis. This one is probably orange, and then there is a blue line for MnO2, which is giving us a really good volume of oxygen produced. It gives us an idea which catalyst is working the best. So which one is working the best according to your idea?
The MnO2.
Right, because it produces the maximum volume of oxygen. So it works the best. Okay, so this is how we can investigate the catalytic action on any reactions. We go with hit and trial method. The best catalyst is the one that gives us the maximum rate of reaction and produces a lot of amount of product in the minimum amount of time. Since we are talking about the speed of reaction, so lesser the amount of time, more the amount of product, better is the catalyst. Now, how does a catalyst work? Not all collisions result in the reaction happening. Collisions have to have at least a certain amount of energy we call the activation energy. If the reaction is slow, it means very few collisions have this energy. When most collision happens, the particles simply bounce off each other. As I've explained earlier, catalysts, what do catalysts do? Catalysts work by providing them an alternate route for the reaction involving a lower activation energy. We can simply say catalysts lower the activation energy for a specific reaction. For example, if the cars have to travel all the way up the mountain and down the mountain onto the other side, it would take a lot of time. Why do we dig tunnels under the mountains? Because these give a very short duration of time for the cars to pass on to the other side. Make sense?
Yes.
So catalyst is actually like drawing a tunnel under a mountain for a faster action. If the activation energy is lower and you don't have to climb all the way up and down, instead you can move straight, you would take a very fast route and finish up your traveling much earlier. The similar is the working of the catalyst. It lowers the activation energy. Many more collisions are likely to be successful. Reaction happens faster. More particles have successful collisions. And now that we have a faster rate of reaction. So what does that do for our reaction? It does not give us a higher amount of product. You need to understand it only provides an alternate route. And actually what happens, everything happens in lesser amount of time. Remember, catalyst is not going to give you a higher yield of product. What happens is that catalyst reduces the time for that yield to happen, for that result to occur. So catalyst provides an alternate route with a lower activation energy. They don't actually lower the activation energy any more than building a tunnel that lowers the mountain. The original route is still there, and if particles collide with enough energy, they will still use it, just as energetic people will still choose to climb over the top of the mountain. So that's a good way of saying it. So catalysts provide an alternate route with a lower activation energy. Now, this diagram would ease up everything for you. Remember, we were drawing reaction profiles or energy profile diagrams in the previous unit? Not in the previous unit, in the previous chapter, my bad. So you had just these reactions drawn in much simpler way like this and this. Now, what are we doing? We are adding a bump for it. Now, this is a reaction without a catalyst, and it has to go through this jump like going through over the mountain without having the catalyst involved in this reaction. What happens when a catalyst is involved in a reaction? Let's move on to the next page to understand that. The catalyst provides an alternate route. So what do we call it? This is the original route, and this is the catalyzed route. With a much lesser amount of activation energy, the reaction can happen easily and much faster, giving us lesser amount of time for the reaction to occur. Make sense?
Yes.
So these graphs are very important. Whenever you have activation energy involved in a reaction profile diagram, try drawing these graphs. You're only supposed to draw those simple graphs if activation energy is not a part of the question. All right? Then you can draw these simple energy profile diagrams. If activation energies are involved, try drawing this kind of jump in the diagram. Adding the jump won't be difficult if you can practice it once or twice. Make sense?
Yes.
Remember that the difference in energy between the reactants and products remains the same with or without the catalyst, and that's the enthalpy change. You would notice this part remains the same whether we have a catalyst or we don't, because this is the same distance between the reactants and the products. This does not change. It's just add this kind of jump or this kind of small jump to the diagram. Make sense?
Yes.
One last small point, catalysts in industry. Catalysts are very important in industrial reactions. Why? Because they help substances to react quickly, even sometimes at lower temperatures and pressures than would otherwise be needed. And at lower temperatures and pressures, we do not have to burn our fuel. We do not have to go with sophisticated equipment. So this saves a lot of money. Make sense?
Yes.
Great. This also finishes the chapter for us.